Welcome to Mini-Lecture 2 for Unit 3. We'll continue talking about radiation today by talking about the full electromagnetic spectrum. So in Mini-Lecture 1 we talked about definitions such as wavelength, frequency, and energy, and recall that we learned that longer wavelengths mean lower frequency, which means low energy. Short wavelengths mean high frequency, which means high energy. So we talked also about the visible spectrum and how red light at about 700 nanometers in wavelength had the lowest energy of visible light, and blue light or violet light had the highest energy of visible light with short wavelengths of about 400 nanometers. It turns out the visible spectrum is only an extraordinarily tiny part of the entire electromagnetic spectrum. So everything on this graph that we look at, from radio waves up through gamma rays, are all electromagnetic radiation. They are all light. It's that our eyes are only sensitive to a very few wavelengths, not to the entire electromagnetic spectrum. So in this mini lecture we will go over the types of light, what they tell us, and how we can observe them. So let's start in the radio waves. Radio waves are not the same thing as sound waves. Radio waves do not carry sound. The way that a radio works is that someone speaks into a microphone. Their sound of their voice is changed into electricity. That electricity is used to generate an electromagnetic wave, a light wave, which we then send out. Your radio receiver picks up that electromagnetic wave and is able to decode it and recover the sound which it produces with a speaker. Radio waves have very long wavelengths. The typical wavelengths of a radio wave run from a few dozen centimeters or so all the way to the longest, which can be meters or even kilometers in length. Radio waves can be as big as us or as big as buildings. If you want to know the wavelength that a given radio is sensitive to, a radio receiver is sensitive to, the length of the antenna is roughly 1/4 the length of the entire radio wave. So a car antenna, which is about a meter long, is listening to radio waves that can be up to 4 meters in wavelength. Moving from radio waves up to the next higher wavelength, we get to microwaves. Now you may have heard of microwaves, and you may think that these are dangerous and energetic because we use microwave ovens to cook food. In fact, microwaves are fairly long wavelengths, as you see here, size of insects ranging from about a millimeter in wavelength to about 10 centimeters in wavelength or so. These definitions are fuzzy. The reason that microwaves can cook food is that water is very good at absorbing microwaves. So a microwave oven produces just a tremendous amount of microwaves, which it then shoots into your food, and the water in the food absorbs that energy and heats up. However, individual microwaves are not very energetic, and so we have microwaves passing through us all the time. Cell phones use microwaves, most radio controls use microwaves, and it doesn't cook us to be around those sorts of things. Going shorter in wavelength or higher in energy from microwaves, we get to infrared radiation. Infrared has wavelengths from between about 1/1,000,000th of a meter to 1,000th of a meter, or from 1 micrometer to 1 millimeter in wavelength. And infrared radiation is produced by warm objects, and we'll talk more about this in Mini Lecture 3. The wavelengths of infrared run from about the size of large single cells, such as amoebas or other protozoa, to things as large as the size of an eye of a needle. Moving to shorter wavelengths yet, we get to visible light. Visible light, as we saw, has wavelengths between about 700 nanometers and about 350 nanometers or so. Again, these definitions are not exact because there's no real difference as we go from visible into infrared. The light acts the same, it's just shorter wavelengths in the visible. And as we talked about in Mini Lecture 1, visible light has wavelengths on the size, again, of single cell organisms. As we go yet higher in energy, we get to ultraviolet light, and now we are getting to electromagnetic radiation that is actually dangerous for human beings. Ultraviolet light has wavelengths shorter than about 300 nanometers or so, which is about the size of virus or even getting down to the size of DNA in our cells. And ultraviolet light is energetic enough to begin to be dangerous to cells. So a little bit of ultraviolet light, we can repair it, but if you get a lot, like in a sunburn, it can be damaging and cause cancer. Going to shorter wavelengths yet, we get to X-rays. X-rays are very small wavelengths, about the size of individual atoms, which means that they have very high energies. X-rays are able to penetrate our skin, which is why we use them for medical imaging, and they are also, because they're so high energy, they can be very damaging, which is why when you go to get an X-ray, everyone else stands behind lead shielding. Finally, the shortest wavelength electromagnetic radiation are gamma rays. Gamma rays have wavelengths on the size of atomic nuclei, so this is about 1/1,000,000th of a meter in size, or even smaller. And these are very high energies. Gamma rays are very dangerous to humans. You don't want to be exposed to them any more than absolutely necessary. At these high energies, the radiation can do a lot of damage. All of these things are the same basic thing: electromagnetic radiation. Here on the Earth, we are lucky to have an atmosphere, and we're lucky not only because we can breathe, but because that atmosphere protects us from the most damaging forms of electromagnetic radiation. So here, notice on this plot, we have changed the wavelength axis, so now the high energies are on the left and the low energies are on the right. So on the left of this plot, we've got the gamma rays, the X-rays, and the ultraviolet radiation. And the plot shows that our atmosphere is opaque to this type of radiation. This damaging radiation does not get through to the ground except with a very little bit of ultraviolet radiation. So therefore, if we want to study gamma rays and X-rays and ultraviolet light from stars or galaxies, we have to launch satellites that will orbit above our atmosphere where that radiation can be seen. When we get into visible light and into part of the infrared band, the shorter wavelength infrared light, this radiation can make it through our atmosphere down to the ground, especially in the case of visible light, which is why we can see each other and why optical visible telescopes can work from the ground, and why we can see the stars at night, because our atmosphere is transparent. When you get into the infrared, there are some regions of infrared light that cannot make it to the ground and others that can. And there are some regions that you can see if you get into onto a high mountain or get into an airplane up above most of the atmosphere. So infrared telescopes are often built on the highest mountains, and we even have a few that are on airplanes. When we get to long wavelength infrared radiation, sort of 100 microns, that's 100 millionths of a meter, to 1 millimeter, a thousandth of a meter, our atmosphere becomes opaque to that radiation again. And not only is it opaque, but the entire atmosphere glows in the infrared at these wavelengths. That's because these wavelengths originate from objects that have temperatures like room temperature. So you and I, your entire room, the walls, the floor, the ceiling, even the air around you is glowing with this long wavelength infrared radiation. So if we want to study this infrared radiation, we have to launch a satellite up above our atmosphere, and then we can cool the satellite down so the satellite itself is not glowing in the far infrared, and then we can study the far infrared light coming from other stars. But we can't study them from the ground because the telescope and everything around it in the atmosphere glow at these wavelengths. When we get to long wavelengths into radio waves, those are again observable from the ground. The atmosphere is transparent. This is why we use radio waves to communicate with cell phones or with our televisions, with satellites. All of that uses radio waves because the atmosphere is transparent. And so we can observe radio waves from the Earth.